Yes, an existing switchboard with 6 fusible switches installed, plus a 200 amp space provision only, with no switch installed, would typically be required to have a main added. The necessity of adding a main to an existing fusible switchboard largely hinges on compliance with the National Electrical Code, or NEC, and local electrical codes. These codes dictate the requirements for overcurrent protection and disconnecting means in electrical systems, especially as they relate to safety and the ability to de-energize the entire switchboard for maintenance or in emergency situations. Firstly, let's define what a switchboard is. A switchboard is a large panel designed to distribute electrical power from one or more sources to numerous individual circuits or loads. It's an assembly of switches, overcurrent protective devices, and buses, typically enclosed in a metal cabinet or structure. Switchboards are commonly found in commercial, industrial, and large residential buildings where substantial power distribution is required. Secondly, consider the function of fusible switches. Fusible switches are a type of overcurrent protection device that uses a fuse to interrupt the flow of electricity in the event of an overload or short circuit. Each fusible switch protects a specific branch circuit or load connected to the switchboard. The presence of 6 fusible switches indicates that the switchboard is already distributing power to multiple circuits. Thirdly, examine the 200 amp space provision. A 200 amp space provision refers to a designated area within the switchboard that is reserved for the installation of a 200 amp switch or breaker. This space is pre-wired and ready to accommodate an additional overcurrent protective device, but currently, no switch is installed. Now let's delve into why a main might be required. The primary reason for requiring a main is to provide a single point of disconnection for the entire switchboard. This main disconnect serves several critical functions. Firstly, it allows for the complete energization of the switchboard, which is essential for safe maintenance, repairs, or inspections. Without a main disconnect, it would be necessary to individually switch off each of the 6 fusible switches to cut power to the entire board, which is cumbersome and potentially dangerous. Secondly, a main disconnect facilitates emergency shutdown procedures. In the event of a fire, electrical fault, or other emergency, a single switch can quickly cut off all power to the switchboard, minimizing the risk of electrical hazards and facilitating a safer environment for first responders. Thirdly, the NEC mandates that switchboards have a main overcurrent protective device to protect the entire switchboard from overloads and short circuits. This ensures that the switchboard's components and connected equipment are protected from damage due to excessive current flow. The specific NEC articles that are relevant to this requirement include Article 408, which covers switchboards and panel boards, and Article 230, which deals with service entrances. These articles outline the requirements for overcurrent protection, disconnecting means, and the overall design and installation of electrical distribution equipment. The requirement for a main disconnect is often dictated by NEC 230.71, which generally requires a building to have no more than 6 service disconnecting means. While the 6 fusible switches might seem to fulfill this requirement, the absence of a main disconnect means that there isn't a single point to disconnect the entire service, which is often a violation. Consider the scenario without a main disconnect. If an overload or short circuit occurs on the main bus bars within the switchboard, the individual fusible switches might not provide adequate protection for the entire board. This could lead to damage to the switchboard components, overheating, and potentially a fire. A main overcurrent protective device, such as a circuit breaker or fusible switch, would provide coordinated protection for the entire switchboard, ensuring that the fault is quickly cleared and minimizing the risk of damage or injury. The 200 amp space provision indicates that the switchboard was likely designed with the intention of installing a main disconnect at some point. The fact that there is a dedicated space for a 200 amp switch suggests that the switchboard's capacity and design anticipated the need for a main. However, the absence of the switch means that the switchboard is not fully compliant with safety and code requirements. When evaluating the need for a main disconnect, it's also important to consider the overall electrical system configuration. If the switchboard is fed directly from the utility service, the requirement for a main disconnect is even more critical. In this case, the switchboard serves as the main distribution point for the building's electrical system, and a main disconnect is essential for isolating the entire system from the utility source. However, if the switchboard is fed from a separate distribution panel or transformer within the building, the need for a main disconnect might be less stringent depending on the specific configuration and the local electrical codes. Even in this scenario, a main disconnect is generally recommended for safety and convenience. To determine the specific requirements for adding a main to the existing switchboard, it's essential to consult with a qualified electrical engineer or licensed electrician. They can assess the existing electrical system, review the applicable codes and standards, and provide recommendations for the appropriate type and size of main disconnect. They can also ensure that the installation is performed safely and in compliance with all relevant regulations. The process of adding a main to the switchboard typically involves several steps. Firstly, the existing switchboard needs to be carefully inspected to assess its condition and ensure that it's suitable for the addition of a main disconnect. This includes checking the bus bar capacity, the enclosure size, and the available space for the new switch. Secondly, a suitable main disconnect needs to be selected based on the switchboard's capacity, the available space, and the specific requirements of the electrical system. This could be a circuit breaker or a fusible switch, depending on the application and the preferences of the electrical designer. Thirdly, the new main disconnect needs to be installed in the designated space within the switchboard. This involves connecting the main conductors to the switch, ensuring that all connections are properly torqued, and verifying that the switch is securely mounted. Fourthly, the electrical system needs to be tested to ensure that the new main disconnect is functioning properly and that the switchboard is operating safely. This includes performing insulation resistance tests, continuity tests, and operational tests to verify the integrity of the system. In conclusion, while the presence of 6 fusible switches provides overcurrent protection for individual circuits, the absence of a main disconnect means that the switchboard likely doesn't meet the requirements for a single point of disconnection and coordinated overcurrent protection. The 200 amp space provision suggests that the switchboard was designed to accommodate a main disconnect, and installing one would enhance the safety, reliability, and code compliance of the electrical system. Consulting with a qualified electrical professional is crucial to determine the specific requirements and ensure a safe and compliant installation. Firstly, consider the existing load on the switchboard. Calculate the total demand load of all the circuits fed by the 6 fusible switches. This will help determine the appropriate size for the main disconnect. The main disconnect should have an amperage rating equal to or greater than the calculated demand load. Secondly, evaluate the available short circuit current at the switchboard. This is the maximum amount of current that could flow during a short circuit condition. The main disconnect must have a short circuit current rating equal to or greater than the available short circuit current to ensure that it can safely interrupt a fault. Thirdly, determine the type of main disconnect that is most suitable for the application. Circuit breakers and fusible switches each have their advantages and disadvantages. Circuit breakers can be reset after a trip, while fusible switches require replacement of the fuse. Fusible switches generally offer higher short-circuit current ratings. Fourthly, ensure that the installation of the main disconnect complies with all applicable codes and standards. This includes the National Electrical Code, as well as any local electrical codes and regulations. Fifthly, properly label the main disconnect to clearly identify its function. This will help ensure that the switchboard can be safely and easily de-energized in the event of an emergency or for maintenance purposes. Additionally, consider the future needs of the electrical system. If there is a possibility that the switchboard will need to support additional loads in the future, it might be beneficial to install a main disconnect with a higher amperage rating than is currently required. This will provide extra capacity for future expansion and avoid the need to replace the main disconnect later on. Remember that working with electrical equipment can be dangerous, and it's always best to consult with a qualified professional to ensure that the work is performed safely and correctly. A licensed electrician can properly assess the situation and ensure the switchboard meets all necessary safety requirements.